Physics students, good afternoon. Mr. Kukut here. In our video today, we're going to be looking at a few problems from your review over test number 4, which is related to Unit 5, which we've covered with uniform circular motion, universal gravitation, and Kepler's laws of planetary motion. Specifically in this video, we're going to be looking at problems number 5 and 6 from your review. If you need any help on problems 1 through 4, and make sure that you check out the other videos we have here available for you. As well, extra copies of your review are available on Canvas, along with the key to those problems. But here we'll be looking specifically at problems 5 and 6. I'll go ahead and start by reading problem 5 for us, and then we'll begin looking at what we need to do. Problem 5 says this: what is the gravitational acceleration, lowercase g, on the surface of the planet Mercury? We're given the mass of Mercury to be 3.30 times 10 to the 23rd kilograms, and the radius to be 2.44 times 10 to the 6th meters. So here we're looking at question number 5. The question is, we want to solve for what we call little g, or local acceleration due to gravity. The acceleration due to gravity in a certain place. And here that place is going to be the planet Mercury. A little bit of an issue there. Now, if you remember from class, we actually came up with an equation for little g. I'm going to show us how we got to that equation again, for those of you that might have missed it or forgotten, and then we'll use that equation to solve for little g on Mercury. So say we have our planet, and we are on the surface of that planet, or roughly on the surface. Again, obviously the picture is not drawn to scale. Now, on the surface of that planet, if we wanted to find the, let's say, gravitational force from the planet pulling on the person, if we knew, let's say if we knew our equation, or if we knew what little g was, the local acceleration due to gravity, we could solve for that. And that's equal to the mass of our person, who, just for reference, I'm going to call object 1 in this scenario, so m1, multiplied by our local acceleration due to gravity. Now, unfortunately, we don't, at least at this point in time, let's say, we don't know what that little g value is. We also have what we call a universal approach to solve for the force of gravity between any two objects anywhere in the universe, no matter if we know the local acceleration due to gravity or not. And that equation looks like this: g times the mass of our two objects. We'll say 1 is the person, 2 is the planet, so m1 and m2, divided by the distance between those objects squared. Now, in this scenario specifically, the distance between the planet and the person, as we've said, is really going to be the radius of the planet, because we're interested in the distance from the center of one object out to the center of the other. And again, because our person is really not this far above the planet, they're really barely above the planet, just, a few 5 to 6 feet. Relatively, it's pretty much going to be just the radius of the planet, would be the distance between objects. So, what we can actually do here is, since we're on the surface of this planet, the local approach should be good to go, right? We can use that if we know little g, and the universal approach is good anywhere. So we can actually set those two equations equal to one another. So here we're going to say that on the surface of the planet, f sub little g is equal to f sub big G. Now, that might not seem like it's going to help us very much, but actually it will. Because we know that the mass of object 1 multiplied by our little g value, our local acceleration due to gravity, should then equal our constant multiplied by m1 multiplied by m2 divided by the distance between the objects squared. Now you'll notice that there is a variable that shows up in both equations in the numerator, which means we can cancel that term out. Technically, in a mathematical sense, we would divide by m1 on both sides of our equation, and because that variable shows up in the numerator on both sides, it will then divide out. So then we'll have an equation for our local acceleration due to gravity, little g, which is our constant, g, times m2, which is the mass of our planet, divided by d squared, where d is the distance from the center of the planet to the surface, or its radius. So now we actually have a proof of our equation, and we can then use our equation, something that we've done in class. So little g is equal to our constant, 6.67 times 10 to the negative 11th power, Newton meters squared per kilogram squared, multiplied by the mass. Here that's going to be the mass of our planet, which we're given to be for Mercury 3.30 times 10 to the 23rd power. And then we'll divide by our distance between objects, which is the planet's radius, squared, which we're given to be 2.44 times 10 to the 6th power meters. And again, as we've talked through, when using, an equation that has a square in the denominator, it's usually good practice to use a second set of parentheses, just so we know we need to square that denominator term first before we divide by the denominator term. So now we can go and plug things in. 6.67 times 10 to the negative 11th power, multiplied by 3.30 times 10 to the 23rd power, divided by 2.44 times 10 to the 6th power. We need to square that term first, and we end up getting a value for local acceleration due to gravity, little g, of about 3.69, maybe round to 3.70 meters per second squared, which, according to what we know about Mercury, is right about where our value should be. So this would mean our value is maybe 2.5 times less than that of the Earth. So effectively what that might mean is your weight on this planet, Mercury, would be about 2.5 times less than it would be on the Earth. So hopefully this gives us some good information on what we're looking for in problem 5. One, how to set up and get the equation for our local acceleration due to gravity, but then how to use that equation if we know some information about the planet that we're on. And as we talked about in class, one of the important things we need to understand about our equation is that the way we find local acceleration due to gravity is based on using information about the planets themselves. Not about the things on the planet, right? And this value is independent of the things on the planet. It is solely dependent on the dimensions of the planet, its mass and its radius. So, hopefully this gets us the information we need for problem 5. We'll now move on and begin to look at question 6. Question 6 says this: Satellite A is in orbit around the Earth and experiences a gravitational force of 2,000 kilonewtons at a distance of d from the center of the Earth. Now, given that we have a lot of information given there, I'm just going to jot down what we know and a little bit of a picture of what's going on. So number 6, we've got, let's say, the Earth, and then a satellite that is orbiting around the Earth at, we're told, some distance. Centralize that a little bit. We're told a distance d, and the force of gravity, the force of attraction between the Earth and the satellite, we're told is 2,000 kilonewtons. And then that's really all we're told about satellite A. Now to continue reading, it says this: Satellite B, with the same mass as A, orbits the Earth at a distance of 4d. What would be the gravitational force from the Earth on satellite B? So now we've got the Earth, and again, this will not perfectly be drawn to scale, but let's say we're now a greater distance away from the Earth. Again, this is not going to be 4 times greater, but just kind of shows us it's a bigger value, and we are at a distance not of d away from the Earth, but of 4d. Now again, that is not drawn to scale. I want us to see it's a larger distance. We're told it's 4 times greater, but I drew this one a little bit large, so it's hard to draw the red circle even larger. Now we're asked this: what is the force of gravity now between satellite B and the Earth? Now, one of the challenges here is that we don't know the masses of the satellites. We do know the mass of the Earth, but we don't know the mass of the satellite, and we don't actually know what the real distance is. We know the ratio between them, d and 4d, but we don't know what that number is. So it can be very, very easy to look at this problem and think, I don't have enough information to solve for the force of gravity, right? Especially if we look at the values that go into our equation. Masses, distances, we don't really know those. But here's what we do know. Let me pan down just a little bit. We know that the force of gravity between any two objects is equal to g times m1 times m2 over the distance between them squared. Now, to make this a little bit more contextualized, I'll say for this is object A, this would be something like the mass of A times the mass of 2, and the distance here is actually D, I'll write that as a capital D, squared. Now, not only changing our equation, I'm just adding a few things into it that make it more specific to this scenario, right? Now, for the second satellite, satellite B, the force of gravity, and again, this is what we actually want to find. The force of gravity would be equal to our constant times the mass of object 1, let's say that's satellite B, times the mass of object 2, divided by, well, this is actually not D, but it's going to be 4D squared. Okay? Now, here's something that we're told. The mass of satellite A and the mass of satellite B are the same. We're also told, well, not told, but we know the constant G is the same, right, in any equation for F sub big G. It's not going to change, it's a constant. And then the second object, object 2. Well, here object 2 is the Earth. It's the other object involved in this a force of gravity, the satellites and the Earth. So here's what that means. In both equations, G is the same, the mass of the satellites, we're told, is the same, and the mass of the Earth is the same. Now, I'm not crossing those out because they don't make any difference. I'm crossing those out for this reason. To draw our attention to the fact that the only difference between satellite A and satellite B is where they are located. Right? Satellite A is a distance of D away. Satellite B is a distance of 4D away. And this is an example of what we talked about in class of an inverse square law. What I want you to see here is this, that our force of gravity is proportional to the inverse, meaning it's an inverse relationship, the inverse square of the distance. And if we know that our objects have the same mass, mass doesn't change, and if we know that the distance is the only term that's changing, we actually can solve for our new force based on this relationship. Now, we should be able to tell this, that if our distance of satellite B is going up, it is a greater distance away, then the force of gravity between the satellite and the Earth should be a lower value. So this value over here that we end up finding should be lower. Here's what we can do. If I look at my equation in red, 4D squared, well, if I square that whole thing, I have to square both values, the 4 and the D. So here, my force of gravity would be all of this numerator, which we'll say is just going to be some number. We don't really know what that number is. Over, well, 4 squared is 16, and D squared would just be D squared. Now my force of gravity here on satellite A is, again, some number in the numerator. Again, let's just, maybe if it helps you, we'll just call it X, right? And this number is going to be the same because all the values are the same, right? The constant and the two masses. So this would be X over D squared. So notice the only difference here is really this, that the force here should be, well, you see a 16 here, and again, there's no coefficient here, so we can assume it's a 1. So here's what this tells us, right? Our denominator for the equation in red is 16 times bigger than for the black equation. So if this value in the denominator is going up overall by a factor of 16, that means the force has to go down by a factor of 16. Right? The only things that are changing here are the distances. The numerators are the same in both equations, and the way I got that 16 is by squaring the 4. So now I can do this. I can take my value for the force and I can divide it by 16. Because, again, the only thing changing is the denominator. It's going up by a factor of 16, and since it's in the denominator, it's inversely related to our force. So I'm just going to take 2,000, right, and I'm going to divide by 16. That's going to give me a value for the force of gravity of 125 newtons. Again, this is a good application of what we call the inverse square law, the relationship between the force of gravity on two objects, or between two objects, and the distance between those two objects. Okay? And as long as we know we don't even need to know the actual distances between them, as long as we know the ratio of the distances, D and 4D. I could have told you those distances were, 20,000 meters and 80,000 meters, right? But again, what I want us to see here is we don't actually need to know those distances. We just need to know the difference between those distances. And that's one of the key things that is very helpful about the inverse square law. It allows us to make determinations on force, depending on the distance. And we can also do that vice versa. if we knew the difference in force between them, we could show that the distance is going to change. If I told you this value was 125, well, I could take 125, 2,000 divided by 125. Notice that was a factor of 16, right? And if this is changing by 16, well, the square root of that would be 4. So the difference here would be d to 4d. We could solve this the other way. So it's a little bit complex in looking at the inverse square law here. What I want us to see is this. We can look at this relationship as a really kind of a ratio of force proportional to the inverse square of the distance. So hopefully this gives us the information that we need for question number 6 on your review. As always, if you have questions, don't hesitate to ask. Seek out help if you need it, and use the resources that are available to you. Good luck.